Welcome back to the show, Russ Jackson. Today we're diving deep into ownership, a core concept in Rust. Can you give us a high-level overview?
Sure, Matthew. Ownership is how Rust manages memory. Unlike languages with garbage collection, or languages where programmers explicitly manage memory, Rust uses a compile-time ownership system. It's safer and more efficient.
So, it's all about safety and efficiency at compile time?
Exactly. The compiler enforces rules, so you don't have memory leaks or dangling pointers at runtime.
Okay, what are these rules? Sounds interesting.
We'll get to the specifics later, but it essentially involves who owns a piece of data. And that ownership has to be correctly transferred between variables or scopes.
Ownership, in a programming context? How does it apply to financial applications?
It's about managing the data behind transactions, investments, and accounting, for example, like ensuring that a user's account balance is valid. Correct management of the data associated with those variables prevents errors.
Interesting. So, how does this ownership relate to the stack and heap?
The stack is fast, for simple, known-sized data. Heap is for dynamic allocations, like large datasets or user data. Ownership deals with how data moves between the two.
So, the stack is like ordered plates, the heap is, well, scattered data?
Exactly. The stack is LIFO, last in, first out. Pushing and popping values is quick, but only for fixed sizes. The heap requires allocating space, which is slower and needs careful management.
You're mentioning allocation. What are the implications of allocating on the heap?
It's a bit like reserving tables in a restaurant. The operating system needs to find space, which takes more time. Plus, we need to keep track of who's using it. Ownership, again, helps with this.
Why is tracking who's using memory so important?
It prevents memory leaks and double-free errors. It prevents a program from using memory that is already assigned elsewhere.
What happens when a function finishes?
Values on the stack are popped off. Variables are cleaned up automatically. If heap data is no longer needed, ownership rules ensure it's deallocated properly.
So, what happens if you don't manage ownership correctly?
Potential crashes, memory leaks, data corruption, bugs, and unexpected program behavior. So, the ownership system is crucial.
So, it's like ensuring the restaurant tables are properly released when finished.
Exactly. Preventing double bookings and making sure resources are freed up appropriately. That is, ensuring that you only have one user at a time managing an account balance.
Makes sense. What are some common misconceptions about ownership?
Some people think it's overly complicated. But once you understand the rules, it's straightforward and makes your code safer, more efficient.
So, ownership is like a safety net for complex memory management.
Yes. A very crucial safety net for robust software. It's like having an excellent, efficient, and robust accounting software.
Thanks for clarifying that, Russ Jackson. A very insightful discussion. Hey, Russ Jackson, welcome back. So, we're diving into variable scope. Can you give us a quick rundown?
Sure, Matthew. Variable scope is like a region of your program where a variable exists and is usable.
Like a little sandbox?
Exactly. Once the variable leaves that sandbox, it's gone.
So, how does that work practically? Give me an example.
Imagine a function. A variable declared within that function is only valid inside that function.
Okay, makes sense. So if I declare a variable outside the function, it's globally accessible?
Potentially, depending on the language and how it's defined.
But in Rust, what happens when the scope closes?
It's deallocated. Rust's memory management is very precise.
What's the deal with string literals?
String literals, like hello, are statically allocated in memory. The variable is valid until the program's end, or a part of the program where it's invalidated.
Interesting. Are there any practical implications in finance?
Absolutely. Imagine managing account balances. A variable holding a balance within a specific transaction would only be valid for that transaction's duration. So, after the transaction is complete, its scope ends, and resources are released.
What about if a calculation goes wrong, and the scope ends early?
The variable will no longer be valid. Very important, especially in high-performance systems.
So, the variable's life cycle is tied to its scope?
Yep, perfectly aligned.
What happens if we try to access a variable outside its scope?
You'll get a compile time error, preventing potential crashes.
Okay, so how does this translate to string, not just string literals?
That's where things get slightly different. String is dynamically allocated, and its scope is not tied to the program's end. Its scope is determined by the code.
So, memory management is more nuanced?
Yes, with string you have to manage its memory. Rust's compiler helps with this, by ensuring you don't use it outside its scope.
And what if a string is passed to a function?
The lifetime of the string inside the function depends on how it's passed.
What happens if I return a string from a function and the function goes out of scope?
That's important, because the string now lives in the scope of the function that calls it.
So, the ownership and lifetime are key?
Crucial. Ownership is about ensuring that a variable is not used after it goes out of scope. Lifetime annotations further specify how long a variable will live in memory.
How does this compare to languages that don't have these rules?
Those languages often leave memory management to the programmer, which can lead to memory leaks.
So, in short, the scope of a variable in Rust is a critical element for memory safety?
Very much so. Careful scope management is a crucial programming practice in Rust, avoiding common programming errors.
Thanks, Russ Jackson. That was very insightful. Russ Jackson, welcome back. Let's talk about copying data in Rust. We've touched on stack and heap, but now you're mentioning clone. What exactly does that do?
Yeah, clone is a powerful method for deep copying. It copies the entire data structure, including any data stored on the heap.
So, not just a pointer, but a whole new copy of the data itself?
Precisely. Think of it like making a perfect duplicate. If you change the original, the copy stays untouched. It's a crucial part of handling data correctly.
Why is this important? Seems like overhead?
You're right, there's a performance cost. It's not free, but in many cases, it's necessary for data integrity. Imagine you're building a financial trading platform. You wouldn't want accidentally modifying the wrong order. Clone guarantees those things won't change by accident.
So, if we just want to modify something, we get another copy?
Yep, you're in complete control. You've got two separate copies. Very important for financial apps, especially.
How does this differ from a simple assignment?
A simple assignment just creates a reference, or a pointer. It only copies that reference, not the data. The pointer points to the same block of memory. If you change something in one, you change it in the other two. It's like two people looking at the same document. One could easily change it, and then the other one sees the change immediately.
So clone prevents that accidental modification.
Exactly. Clone makes a separate copy.
What's a scenario where you might not want to use clone?
If you're just doing calculations and don't need independent copies. If you're working with large datasets, avoiding unnecessary clone calls can save on memory and compute time. You'd use references, or borrowing, instead of creating new copies.
Okay, so clone is a deep copy. Assignment is a reference copy. You're making it very clear.
The choice depends entirely on the context. In financial applications, deep copies like clone are fundamental for accuracy and avoiding bugs.
You mentioned performance implications. How can we manage that?
You can optimize using clone when absolutely necessary. There are ways to optimize for performance in that scenario without compromising on safety and accuracy, which is critical in financial systems.
So clone is a deliberate choice when you need data independence, especially critical in financial systems.
Absolutely. A deep understanding of how these operations behave and when to use them is crucial for writing safe and robust Rust code, whether for finance or other applications.
Excellent points. So clone makes a whole new copy of the data on the heap. It's not automatic, you have to explicitly call it. It's important to think about the implications for both performance and data safety. We'll dive deeper into these techniques in subsequent episodes. Thanks, Russ Jackson.
Thanks for having me, Matthew.
Russ Jackson, thanks for joining us today. We're diving deep into stack-only data in Rust. Can you explain what that means?
Sure, Matthew. Stack-only data means values are stored directly on the stack. Think of it like a stack of plates.
So, no memory allocation needed?
Precisely. For things like integers, That's how it works. It's super fast because the computer knows exactly where to find it.
So, if I copy an integer, it's a fast copy?
Yeah, it's a completely separate copy, but the original remains valid. No need for clone. Rust's smart about that.
What makes it different from, say, a string which needs memory allocation?
Strings are dynamic size and frequently need memory management, making them different.
Interesting. You mentioned the copy trait. Can you unpack that?
The copy trait tells Rust that the type can be copied quickly.
Like just creating a duplicate? And it avoids the whole cloning business?
Exactly. Rust can make a copy easily, without needing to worry about deep copies or resource management, just like in normal integer cases.
So, what if a type needs special handling when it's dropped?
If a type implements the drop trait, it needs special cleanup when it goes out of scope. If you try to copy it, it won't compile.
So, drop implies needing to free resources like memory blocks?
You bet. Trying to copy a string, which might need deallocating, is a bad idea. It will cause a compiler error.
Okay, that makes sense. So, what types are typically copied?
Integers, booleans, characters, floating point numbers, generally simple scalar values. Tuples can also be copy if all their elements are copy.
So a tuple like 1, 2 is easily copied, but 1, hello, isn't?
Correct, you see why. The string part needs more careful handling when it goes out of scope.
Right, so you need to understand if a type needs drop to know if it's safe to use copy.
Exactly. Always check the documentation to be 100% sure.
What happens if you try to copy something that shouldn't be copied this way?
You get a compile time error, which is great.
What are the practical financial implications of this?
In financial apps, you might use copy for things like transaction IDs, integers. Copying them is a very cheap, fast operation.
But not for complex financial instruments like options contracts, right?
Correct. Those would need more detailed management. Understanding copy is about optimizing performance.
How might this affect financial data structures or algorithms, then?
It affects the speed and efficiency of data manipulation. The design decisions impact whether or not copying becomes very fast.
So in short, if your financial data structure relies on integers, use copy traits for faster operations?
Absolutely. For scenarios that rely on integers, copy traits can drastically improve efficiency.
Very insightful, Russ Jackson. Thanks for taking us through these concepts.
My pleasure, Matthew.
Welcome back to the show, Russ Jackson. We're diving deeper into Rust's ownership model today. So, we've been talking about how values are moved. What's the deal with returning values?
Right, Matthew. Returning values can also transfer ownership. Think of it like handing over a physical object. When you return a string, you're effectively giving it away.
So, it's a kind of transfer of responsibility?
Exactly. If a function creates a string and returns it, the ownership of that string moves to the caller. It's important because Rust prevents double freeze, a common memory error.
Got it. So, that example you showed with gives underscore ownership and takes underscore gives underscore back. It's all about this ownership transfer?
Precisely. The gives underscore ownership function creates a string, then returns it, effectively giving ownership to the caller. Takes underscore back does the same, receiving the ownership from the caller and then passing it on in the return.
Okay, so if we're not careful, a value can vanish from a function, right?
Absolutely. If a variable is moved, it ceases to exist in its original scope, and a new scope takes over. This can feel a bit quirky to programmers accustomed to passing values by reference.
That's a significant difference from other languages. What about situations where we need to use a function result without transferring ownership? Or do multiple returns?
That's where tuples come in handy. We can return multiple values, packaging them together as a tuple, but still the underlying variable ownership transfers.
Oh, so we're not losing the original value?
No, but the important thing is the ownership is transferring. If we want to avoid moving ownership completely, we use references, which we'll get to next.
So, returning multiple values is more common than we first thought, as long as we correctly use tuples rather than references?
Yes. Returning tuples is useful, but we can also have multiple return types. So, keeping track of ownership becomes important.
You mentioned references. Can you elaborate on why those are important for avoiding ownership transfers?
References allow functions to use values without taking ownership. They provide a way to work with data without permanently moving it. This avoids the hassle of moving and returning values back.
Why would we not use a reference? Why would we move a value instead?
Moving can be advantageous when you want the function to have exclusive access to the data. Imagine needing a copy and potentially modifying the underlying data. Then you want to take ownership and create an owned copy. For example, in financial modeling, sometimes you need to modify data. Otherwise, use a reference.
So, the choice between references and moving is about control and exclusivity versus sharing, right?
Exactly. It's a trade-off between sharing and exclusive control. In financial applications, you might want exclusive control if you're performing complex calculations. But if you're just accessing data, a reference is ideal.
That's helpful. So, now we see how ownership interacts with multiple returns and avoid the overhead of passing/returning data. Is there a way to give an object to multiple functions without giving away ownership?
Absolutely. We'll explore references and borrowing in the next segment. Those mechanisms allow functions to work with data without requiring ownership. It's like letting a colleague borrow a tool for a specific task without permanently taking it away.
Great. Looking forward to it. Welcome back to the show, Russ Jackson. Today, we're diving deep into mutable references in Rust. Can you give us a quick overview?
Sure, Matthew. Mutable references are like, special permission slips to change something in your code. But there's a key rule. Only one person can hold that permission slip at a time within a certain block of code.
So, one mutable reference at a time? Why that restriction? What are the potential pitfalls if we don't have this rule?
Imagine two people trying to simultaneously edit a spreadsheet. Chaos ensues, right? One person might overwrite what another has done without anyone knowing. That's a data race, and Rust prevents them at compile time. No more runtime surprises.
Got it. Can you give us an example of a mutable reference and how it works?
Let's say we have a variable, like a string, hello. We want to add world to it. We can create a mutable reference to this string. By having that mutable reference, we have the permission to change the content of the string. Once this permission is used, we need to return the permission.
So, if we try to create another mutable reference to the same variable within that same scope, the compiler flags it?
Precisely. Rust throws an error because it's like trying to give two people the same editing permission simultaneously. It's a safeguard against potential data corruption.
Okay, that makes sense. What about immutable references?
Immutable references just mean read-only permission. You can have many immutable references to the same data because they can't change it. Think of them like observers, only reading data, not affecting it.
And combining mutable and immutable references?
Combining them is tricky. If you have an immutable reference, then a mutable one comes along. You can't have both at the same time. Imagine a reader and an editor wanting to access the same spreadsheet, but the editor needs exclusive access.
So, having multiple immutable references is okay, right?
Correct. Because they can't change the data, there's no risk of overriding another reader's view of it.
What if we create multiple immutable references and then a mutable reference?
You get an error then, Matthew. The immutable references have the right to the data, and mutable wants the same access, causing a conflict, and the compiler steps in.
So, the compiler is like a watchful guardian, preventing data races and ensuring the correctness of our code, right?
Absolutely. It's a proactive way to avoid subtle errors that can be very hard to debug in other languages. It's all about preventing those runtime surprises.
Let's say we have a more complex scenario, a shared resource being used in a financial transaction where we want to ensure the safety of that data. How do mutable references play a role there?
In a financial application, a mutable reference would be like the transaction processor. Only one transaction processor should be able to change the account balance at any given time. Immutable references are used for monitoring the balance.
How would Rust handle that?
Rust ensures only one transaction is allowed to mutate the balance simultaneously, preventing overriding or race conditions that could lead to financial irregularities. It's all about safe and secure transactions, you know.
So, mutable references are key to preventing these types of issues in financial systems.
Exactly. They force you to think about how your code manipulates data and avoid potentially disastrous race conditions.
Thanks, Russ Jackson. We've learned a lot about mutable references today.
Thanks for having me, Matthew.
All right, Russ Jackson, thanks for joining us. We were just talking about mutable and immutable references. So, what's the deal with these slices?
Yeah, slices are a powerful way to work with parts of data structures, like arrays or strings. Think of them as a view into a larger collection, not a copy.
A view? Like a window into the data?
Exactly. They don't own the data, they just refer to a portion of it. That's crucial for performance, especially when dealing with big data sets.
So, how do they differ from, say, a full reference?
A regular reference points to a single element, whereas a slice points to a range of elements. Imagine you have a long list of numbers. A slice lets you work with just a few of them together.
That makes sense. How do slices relate to the rule about having only one mutable reference?
The immutability rule still applies. You can have any number of immutable slices. But only one mutable slice can exist at a time if the underlying data is being shared.
So, you're saying if you have a slice of numbers, you've got that window, but a single mutable window on the same list only exists at any given moment?
Precisely. Think about it like a team project. Multiple people can read the code, immutable views, but only one person can edit it at a time, mutable view.
Makes sense in terms of data integrity. Any practical examples in finance?
Absolutely. Imagine a large transaction log. You might want to slice a portion to quickly analyze recent trading activity. You wouldn't want multiple people simultaneously altering that segment, hence the rules.
Okay, so slicing lets us look at a portion of a bigger data set without copying everything. So, how does slicing affect performance?
Big time. Copying a large dataset is slow. Slicing avoids that, so operations are faster. Critical in high-frequency trading, where milliseconds matter.
So, what are some common errors people make with slices?
One mistake is trying to create a slice beyond the bounds of the original data, like accessing a value that isn't there. That's a runtime error, not something the compiler handles.
So, basically, if you try to access a part of the list that doesn't exist, it crashes?
Yes. Always validate your slice indices to avoid those nasty crashes.
That's valuable context. Let's imagine a situation where you have multiple slices of a large dataset. Can you provide an example of how to handle conflicts if one slice needs to be updated while another is in use?
You'd need to ensure the updated slice doesn't overlap with the currently in use slices, which is often handled by using immutable slices for read operations while managing any update in a new section of memory. That way, you have a consistent view for any operation being performed.
Thanks for this valuable insight. I've got a much clearer picture now of slices in Rust and how they relate to overall performance. Welcome back to the show, Russ Jackson. Today, we're diving deep into string slices in Rust. Can you lay the groundwork for us?
Sure, Matthew. We've been working with strings and their references, but what if we want to work with a part of a string, not the whole thing? That's where string slices come in. They're like a window into a section of a string.
So, a window into a string? Interesting. And what's the problem with using the index alone, as we saw in the previous example?
The problem is, if you store a single index and you modify the original string, the index becomes invalid. It's like having a street address for a house. If they move, that address is no longer valid.
Got it. So, a slice solves this issue by linking the piece of data to the original string. How exactly does it do that?
A slice doesn't own the data. It refers to a part of an existing data structure. It holds the starting and ending positions, and it maintains a link to the underlying data.
That makes sense. So, how would you return just the first word of a string, avoiding that index invalidity problem?
Instead of returning the index, a string slice lets us return the part of the string itself.
So you return the actual string value instead of a number. That's a major improvement. Can you explain how string slices are declared?
String slices use special syntax. You use a reference to the string. You'd use something like a reference to a string from an index to another index to specify the start and the end.
You mean like a range of the string?
Precisely. Think of it as a view into the string, without taking ownership.
Okay, so we can avoid that problem of the index becoming stale. That's huge. How would this improve efficiency in financial applications, say tracking stock prices?
In financial data, you might want to extract parts of a log file or specific price ranges for analysis. Slices would allow for efficient retrieval of that data without issues of index inconsistency.
You mentioned ownership earlier. Can you elaborate on the concept of ownership in the context of string slices?
Slices don't own the data they reference. The original string owns the underlying data. Slices just point to a location in that string.
So, the string remains intact, and the slice simply views a portion of it. Makes sense.
Exactly. The flexibility and safety of slices make Rust very well suited for tasks requiring efficient and safe data manipulation.
How does Rust handle potential issues with slices referencing invalid memory locations?
The compiler enforces rules. A slice must always point within the bounds of the original data. Any attempt to create a slice exceeding the string's bounds would lead to a compilation error.
So, using slices is safer and more efficient than the index-based approach by not copying the underlying data into another variable?
Precisely, Matthew. You're gaining better performance and safety.
What are the common pitfalls or misconceptions around using string slices in Rust?
One common mistake is trying to modify a slice in a way that affects the underlying string. This can lead to surprising or even incorrect results. It's vital to understand that the slice doesn't take ownership of the data.
Thanks for that overview, Russ Jackson. It really clarifies the power and safety of Rust string slices. Great stuff. Russ Jackson, welcome back. Today we're diving into string slices. Can you give us a quick overview?
Sure, Matthew. String slices are like a window into a string. They don't own the data. Think of a pointer to a portion of the larger string.
So, they don't copy the whole string? That's efficient.
Exactly. This is crucial for performance, especially when working with large strings in financial applications. Imagine tracking stock prices. You don't want to copy massive datasets.
Okay, how do we create these slices? Show me an example.
We use the slice notation. Let's say you have a string literal, hello world. You can create a slice from the first to the fifth character using and hello world 5.
So, it means reference. That's key.
Precisely. The reference allows you to work with the original string, but without copying.
You mentioned string values too. How do slices fit in there?
You can get a slice from a string too, using the syntax. And importantly, you can pass those slices directly into functions. Very powerful.
So, what's the benefit of using slices as function parameters?
It makes functions more versatile. Instead of having separate functions for string and str, you can use one function for both, which is amazing.
That's reusable code.
Yes, reusable code, and it prevents unnecessary copies.
Wait, what if the slice goes out of bounds?
Rust will prevent that. It's a critical safety feature. If you try to access a character beyond the bounds, you'll get a compile time error.
What's a real-world example in finance?
Imagine parsing stock tickers. You might want to extract the stock symbol as a slice of the ticker string.
Okay, how do you extract the first word in a string using slices?
You use a slice and a function. For example, the first underscore word function in the code example will extract the first word from a string or string literal, or a slice.
That seems cleaner. Why the change in how you use the string values?
To use the same function to handle string literals and string objects, instead of different string functions.
So, you get the same functionality with less code. Clever.
Precisely. You get flexibility and efficiency in one.
Are there any pitfalls using string slices?
If the original string is mutated after getting the slice can become invalid. You need to manage lifetimes properly to avoid these issues.
So, careful management is crucial.
Absolutely. Understanding the lifetime of borrowed data, and slices specifically, is essential in safe Rust development.
So, string slices are more general, save memory, and give better code organization.
Correct. Excellent tool to have in your toolkit, especially in performance-sensitive financial apps.
Great explanation, Russ Jackson. Thanks for tuning in. Russ Jackson, welcome back. We're diving deeper into Rust's powerful array handling today. Can you explain these slices?
Sure, Matthew. Slices are like zoomed-in views of portions of an array or string. Think of a spreadsheet. You might want to focus on a specific column or row.
So, how do they work?
They're references, meaning they don't copy the data. They just point to a part of it. This saves memory.
So, you're saying they're like pointers but for sections?
Exactly. They hold a pointer to the first element and a length. This is super important for efficient data handling.
Why is this important practically speaking?
Imagine working with large datasets. Copying the entire dataset would be slow and waste resources. Slices let you work with specific parts without unnecessary copying.
How do we create these slices? Give an example.
You use the square bracket notation, like an A1, 3, specifying the starting and ending indices.
So in that example, an A1, 3?
Yes. This creates a slice referencing elements at index 1 and 2 of the array A.
How does this relate to financial applications?
Imagine you have a huge dataset of stock prices. You can use slices to analyze a particular time period of stock data without loading the entire set, drastically improving performance.
What happens if you try to access an element outside the slice's bounds?
Rust is super safe. It prevents this. This is a critical aspect of Rust's safety.
What are potential pitfalls when using slices?
You have to be careful to avoid exceeding the slice's boundaries, or you'll get a runtime error.
Is there a difference between string slices and array slices?
Yeah, there's a fundamental difference. String slices have some added complexities related to UTF-8 encoding, ensuring string validity.
So, a slice is just a view, not a copy of the underlying data.
Exactly. This allows for efficient manipulation of data.
How does it impact memory management?
Slices themselves don't consume a lot of memory.
So, why not always use slices? Are there limitations?
Well, you can't modify the original data directly. You're only viewing part of it.
Interesting. So, you're just giving a view of the data, not making a new copy.
Correct. This saves memory, but modifying the underlying data would require different techniques.
Thanks, Russ Jackson. This was incredibly helpful.
Anytime, Matthew.
Russ Jackson, thanks for joining us today. We're diving deep into Rust's memory management, something crucial for performance and safety. So, ownership, borrowing, and slices. Can you break down how these concepts interact?
Absolutely, Matthew. Ownership in Rust is like a property deed. One thing owns the data, and it's responsible for its lifetime. That's how Rust prevents dangling pointers, the dreaded errors where you try to access memory that's already been freed.
So, it's not just about preventing memory leaks, but also making sure data is valid while it's used?
Exactly. Borrowing is like temporarily lending a book. You have permission to read or even modify it, but the original owner still has the final say on its fate. Slices are like taking specific chapters out of that book. They don't own the book, but they work with a portion of it.
Interesting. Can you give a real-world analogy? Imagine a financial transaction, for example, transferring money from one account to another. How would ownership come into play?
Sure. The original account owns the money. When you transfer, it essentially gives a temporary, read-only borrowing to the receiver to see how much to deduct. Only once the debit is confirmed does the receiver take ownership of that amount, within the context of the transaction.
So, the original account releases its claim on that amount during the transfer?
That's right. And the entire process is tracked and checked by the compiler. It ensures only the account with the money makes the change.
How would this prevent issues like double spending?
Because the original owner is the one deciding to let go of its claim on the money, the transfer, and only one account, the receiver, takes possession.
What about slices in this context?
Imagine slicing a portion of that transfer data for auditing. The slice doesn't own the transaction, but accesses a certain portion for that purpose.
That's pretty neat. What are some common misconceptions about ownership?
Some folks think you have to copy every piece of data. But ownership in Rust is about responsibility, not always duplicating it.
So, you're saying sometimes borrowing is faster than copying in some cases?
Precisely. That's why slices are so critical. You can work on portions without copying the whole thing, and this optimizes speed, like a bank transfer.
Right, so ownership in Rust is about efficient and safe memory management.
It's more like an intelligent system of accounting that avoids errors at compile time. It ensures the money is where it should be, when it should be there.
Excellent explanation, Rustjection. So, ownership, borrowing, and slices are all interconnected tools for building robust and performant systems, even in a financial context. Thanks for clarifying that.
My pleasure, Matthew. We'll delve deeper into structs in Chapter 5. It's all about how these concepts allow us to structure and manipulate data, making our programs safer and more efficient.
Looking forward to it. Great stuff.